Hello, how are you everyone? Okay, just let me know if everything is good. Audio, video, everything is fine, right? Okay, so let's get started. So, so now we will see, contours and gradient descent. These are two small topics, and we will see these two small topics. And once these two small topics are covered, then we will go to the machine learning, core machine learning topics like regularization, ridge regression, and these things. Okay. So please let me know if everything is fine. Okay, great. So let's get started. So now in this lecture, we will see contours and gradient descent. But before that, tell me how was your AIMT today? So today we had AIMT. Have you attempted AIMT? Has anyone attempted here? There has been huge participation. The number of people who have attempted today AIMT was 800. So it was a huge participation. Have you attempted? Let me just ask you. Okay, because you might not have prepared for all the topics, so that is why I'm asking. Okay, great. Yes. So result अभी आने ही वाला है. At 6:30 result will be there. Okay. So let's get started now. So we will start a topic which is called contours. It is a small topic. Contours is very small topic. And then once this is covered, we will have our next topic which is called gradient descent. Okay. So let's get started. So see here that you have any, let's suppose you have any curve, okay, which is like this. So basically, let me just tell you, it is a function. So for example, this, let me just take this example. For example, this is a function which is a function of two variables. See, if I have function of one variable only, then I will be having something like this in 2D. See, let's suppose if I have function of one variable only, y equal to x square, then it will be in 2D. Why? Because one of the axes will be taken by x and another axis will be taken by y, right? So there are two axes. One is taken by x and another is taken by y. So if the function is just 1D function, then still you will be representing that in 2D, right? If the function is just having one variable, still it will be in 2D. So if I just ask you that given this function, this is a function in two variables, right? One is x, another one is, let's suppose, y. And now on the z axis, on the vertical axis, let's suppose we are having on the z, we are having the function value, which is basically fxy. Okay, z is nothing but fxy. For example, let's suppose this function is x square plus y square. Okay, or x square minus y square, or it could be anything. Okay, I do not know exact function. Suppose this is x square minus y square. Okay, then for some value of x and y, this will be, let's suppose for x equal to 1 and y equal to 2, then it will be 1 square. If x is 1, if you are putting x as 1 and y as 2, then it will be 1 square minus 2 square, right? Something like this. So 1 minus 4, it will be minus 3. If x is 1 and y is 2, it will be minus 3. Is this fine to everyone? Now similarly for different values of x, there will be different values of z, right? So if x is, let's suppose, this, and y is this, and then z is something like that. There are different possible values of z. So basically the curve will look like this. Okay, curve will look like this. Now what are the contours? So today's topic is basically contours. What are the contours? It is a nicer way to visualize these curves. Okay, so suppose you have this particular function, this particular curve. So contours is a nicer way to visualize it. Okay, contours is a nicer way to visualize. So how we are visualizing, let me just tell you. So for example, let's suppose you have some function. Okay, this is one function which is in x and y. So you have x axis, you have y axis, and then you have z axis. On z axis you will be having its values. Okay, so x and y are the input variables. X and y are the input variables. X is input, y is input, and then z is basically something which is output. Okay, which is basically fx. So z equal to fxy. Now, what does contour does? It basically says that let's just cut it for the fixed value of z, right? I mean, you just fix some fixed value of z. For example, z equal to k. For example, you are fixing z equal to, let's suppose, 100, or let's suppose z equal to 20. For z equal to 20, you will be cutting it. You just need to cut it. Okay. So just cut this, cut this, cut this, cut this, cut this. So if you cut this, you will be getting a circle. You will be getting a circle. So this circle is here, right? So one cut is basically for one fixed value of z. Is this fine to everyone? So see that this is a cut, and which is for the fixed value of z. This is another cut which is for the fixed value of z. So basically you are cutting here, right? This is for the fixed value of z. You are cutting here. This is for the another fixed value of z. So there are different circles that you are getting, but there each of this circle is basically one fixed value of z. Which means that let's suppose you're cutting here, and here z is, let's suppose, 20. Okay, here z is 20. Then you will be getting one circle. This is the circle that you will be getting. This circle will be having all the points on this circle will be having z equal to 20 only. All the points. So suppose you are cutting at 20, then all the points on this circle will be having k equal to 20 or z equal to 20. Okay, all the points on this circle. Are you getting a little bit? So basically what I'm trying to say, that you are going to cut it. Okay, you are going to cut it, and then you are going to get some shapes. So for example, these circles. Okay, these circles, and each of this circle, interestingly, each of this circle that we have is for one fixed value of z. This is important. Okay, each of the circle is for one fixed value of z. Is this understood to everyone? Because this is very important. Okay, so basically you are going to cut it, right? Similarly, if you see this, then you are going to cut it, right? You are going to cut it. Okay, so you will be getting circles. So for example, if you're cutting it here, then for z equal to 1 there will be one circle. For z equal to 1 there is one circle. And then if you're cutting it z equal to 2, then for z equal to 2 there is another circle. Okay, now similarly you will be, so you have something like this. You will be cutting, and then you will be getting different circles. Okay, little bit you might have understood, right? Suppose you are having this, and then you will be cutting, and then you will be basically having different circles. Now you notice one thing. See, here z is increasing, right? I mean, z axis is this. This is x and y. Okay, this is xy plane, and z axis is this. Now this, for higher value of z, at this graph, for higher value of z, you are getting a smaller circle, which means this inner circle is basically for higher value of z. Are you getting my point? Here, let's suppose z is 100. So this inner circle is for z is 100. And then this circle is for lower value of z. So outer circles, so the moment you are going outside, right, the outer circles are for smaller values of z. For example, this is, let's suppose, z equal to 5. So one circle corresponds to one value of z. Is this understood to everyone or not? Okay, so this is important to understand, that one circle corresponds to one value of z. And now in this particular example, it so happens that innermost is the highest value of z. But interestingly, if you see this example here, this smaller circle, can you tell me that this smaller circle, let's suppose if I say that this smaller circle is z equal to, whatever, let's suppose z equal to any value. Okay, then the moment you are going outside this, if I just compare between these two, okay, let's suppose this is z equal to a and this is z equal to b. Can you tell me whether a is greater than b or b is greater than a? Can you tell me this, whether a is greater than b or b is greater than a? Which means this inner circle is for the smaller value of z, or the outer circle for the smaller value of z. Here in this case, interestingly, this outer circle is for the higher values of z, right? Because the moment you, this is the z axis, right? The moment you go up, you will be getting the higher values of z. So outer circle is for the higher values of z. So that is why you will say that this, yes, I got the correct answers. So this is the answer here, right? This is the answer. So basically, it will depend on the shape, that whether the inner circle is the higher or like that, right? I mean, we might not always get the circles. Okay, I will tell you other examples also. But yeah, the final value will depend on the original shape. Okay, whether this value is greater or this value is greater, it will depend on the original shape. For example, here this value is 100 and this value is 5. Why? Because the inner circle is larger here. Okay, but here the inner circle is smaller. Are you getting my point? So basically contours are nothing but, these are called contours, are nothing but cut. Okay, you're taking the cut, that is just contour. So here we are getting inner circles for the smaller value of z, and outer circle for the higher value of z. Okay, this is another graph. This is x square minus y square. Okay, earlier one, this was not x square minus y square. I've just written like x square minus y square there, I think. Okay, it is not x square minus y square, it could be minus x square minus y square, something like this. Okay, so basically what I'm saying, that that the final shapes could need not to be circles. Okay, for example, if this is x square minus y square, okay, this is a very interesting shape. Here if you cut it, right, here if you cut it, then you will be getting, for one cut you will be getting something from here, something from here, and something from here. Okay, so you will be getting one 2D curve which is like this. Okay, for one cut you will be getting something like this. Okay, so here we are not getting circles. Understood? I mean, we do not need to always get circles. Interestingly, here we are getting very weird shapes, right? For one cut, we are getting four circles, right? One, two, three, four. For one cut, we are getting four circles, something like this. Okay. So these are the contours. You do not need to make the contours. You just need to understand them. Okay. In exam, they will not ask you to make the contours, but they will ask you to understand it. How they can ask the questions? I will just tell you. Okay. I will just tell you that what kind of questions they can ask you. Okay. Similarly, Similarly, here we are getting very weird shapes, right? These are the contours. Now, in all of this, one thing is common, that one contour line is for one fixed value of z. Okay, this is fixed. For one contour line, the value of z is fixed. Okay, the value of z doesn't vary. This is a very important property. The value of z doesn't vary. It is fixed for one contour line, right? Similarly, here we are getting again some weird shapes, right? Two circles, I think we are getting, or something like this, right? So you do not need to make contours, as I told you, just need to understand them. So now we will just try to understand them. Okay, we will just see that what kind of questions they can ask. For example, let's suppose this is a function x square minus y. Okay, they are saying just draw the contours for these values. Okay, so how to draw the contours for these values? For example, x square minus y. Okay, for a fixed value, we will be drawing the contour. So this is going to be y equal to, you can write it as x square minus k, right? Now, which means for k equal to minus 2, for k equal to minus 2, it is y equal to x square plus 2, right? Similarly, for k equal to minus 1, it is y equal to x square plus 1, right? So basically, for different k, there will be different y values. Now you can just plot it, right? You can just plot it. For example, if you just plot this, right, then how will it look like? Let me just tell you. Okay, so it will look like this: x square plus 2. So it means that maybe it is, if for x equal to 0, y is 2, right? For x equal to 0, y is 2, maybe it is little up, little shifted, right? This is one contour for k equal to minus 2. For k equal to minus 2, you got this contour. For k equal to minus 1, you are getting this contour. Okay, for k equal to minus 1, you are getting this, like that. Okay, for k equal to, let's suppose, 0, for k equal to 0, it is x square, you will be getting another contour. So basically this is very first example where we are drawing the contours. Okay, although you don't need to draw it, if they ask you, then it will be very simple. How to draw it? You just need to put the fixed value of z. Just need to draw the just need to put the fixed value of z, and then you will say that, okay, this is your general equation. The moment you vary this k, you will be getting different contours. So here you are getting these different contours. Is this fine to everyone? Is this fine to everyone? Okay. So someone is asking that, is this course enough for Gate DA? Yes. So if you are following these lectures, maybe you can definitely try following these lectures. We will be covering as many as possible machine learning algorithms. Okay. So you can definitely follow these lectures. Okay. So this is easy, right? Now let's just have a very important convention, which is that when we are making the contour plot. Okay. By the way, you notice one thing. You notice one thing here is that the z values, if I'm taking minus 2 and then minus 1, z values are basically equal interval, which means only one difference here. Okay. If I just ask you the difference between these two, 1, then difference between these two are 1, then difference between these two are 1. So basically here we are getting equal difference, right? I mean, it's not like if I'm drawing the contour for k equal to 2 and then suddenly I'm drawing the contour for k equal to minus 1 and then for something else. Okay, so basically this should be the equal difference. If this is 1, then this has to be 1, this has to be 1, and like that, right? The difference is equal. Why that is the case, that I will tell you. So basically you can draw for different values of k, but we don't do it. because that will defeat the purpose of making the contours. So we make the contours for the equally spaced values of k, then only it is helpful for us. Okay, I will tell you that what does this mean. Oh, don't worry. So basically, let's just have the convention in place first, that we make the contours plot that are always equally spaced, okay, or for the values of z. For example, we might choose -2, -1.5, and then we have to choose afterwards, we have to choose zero point 0.5 difference only. Okay, afterwards we have to choose zero point 0.5 difference only. Now, however, the level curves and contours are the same thing, by the way. Okay, level curves and contours are the same thing. Themselves are not usually spaced, not usually equally spaced. What does this mean? I will tell you. Okay, so let's just have this example. This example. Let's suppose. So suppose this is some function, and I'm making the contour of this function. Maybe I have this example there. Let me just check. Okay. So let's just have this function which is like this, right? So if you're making the contours, now if you put in this particular function, if you put, let's suppose, this is 9 minus x square minus y square. Okay, if you put, let's suppose, equal to k. Now for k equal to 0, you will be getting x square plus y square equal to 9. So probably you will be getting something like this, right? You will be getting something like this. And then for k equal to 1, you will be getting x square plus y square equal to x square, sorry, let me write step by step. X square 9 minus x square minus y square equal to 1, and then x square plus y square equal to 8, right? Equal to 8. So for k equal to 1, you are getting something like this. Now interestingly, for k equal to 2, now you will be getting 9 minus x square minus y square equal to 4, right? If k is 2, then taking the square will be 4. So it will be x square plus y square equal to 5, right? So earlier, just before that, see what I'm trying to say, that if you are putting different values of k, there are two things that I want to explain here. Let me go step by step. See, suppose this is the function. Okay, for this function you want to draw the contours. Now this is 9 minus x square minus y square. Okay, let's just keep it as k. Now you will say this is same as x square plus y square equal to 9 minus k, right? This is same as like this. Now for k equal to 0, okay, for k equal to 0, it is x square plus y square equal to 9. For k equal to 1, it is x square plus y square, I think this is k square, right? X square plus y square equal to 8. Now for k equal to 2, it is x square plus y square equal to, this will be 4, 9 minus 4 is 5, right? 5. So initially, since it is going through 3, 0, because it is 9, and then the first is x square plus y square equal to 9, then second one is equal to 8, then third one is directly 5. So see here, the k values are equally spaced, isn't it? The k values are equally spaced. So basically the k values are for 0, 1, 2, 3 like this only. But the real contours, okay, they need not to be equally spaced. Ultimately, we are getting 9 here, 8 here, 5 here. So that's what this line is saying. That however the level curves of the contours themselves not usually equally spaced. Okay, they need not to be equally spaced. Understood? So k values here that we are getting, okay, k values are actually equally spaced, right? But these contours are not equally spaced, and this is very important. Okay, so basically you will get to know that the closer the contours are, this will tell you something very nice property which is called steepness, that how fast, see here, if the contour is close, then what does this mean? Okay, let's just look at this x. Let's just look at this particular you know uh, point. Let's suppose you are at this point where x is, let's suppose, some something, let's suppose, lesser than 3, which is, let's suppose, 2.5 or something. Okay, and y is, let's suppose, 0. Suppose you are at this point. Now you are basically going to this point by increasing the x. Suppose you made x equal to 3 and y equal to 0 only, right? So basically you just little bit changed here. Okay, you just little bit changed here. Now if you notice that even if you are doing little bit change, your z value, these are the z values, right? I mean, these are the z values. So your z value, okay, just by little bit changing x, your z value is actually jumping by 1, right? Your z value is jumping by 1. But here, if you are here, then you have to change x too much. To change z value 1, you have to change x too much, isn't it? See, we are keeping it equally spaced just to see that if I want to go from here to here, how much effort I need to make just to make the same change. Okay, if this change is 1, and since these are the, I mean, k values are equally spaced in the sense that we have taken numbers which is 0, 1, 2, 3 like this only. It's not like the like that we can't compare. So basically we can compare these three. Given these three curves, you can compare one thing for sure, that if we are here and going from here to here is too much effort, too much change in y. Okay, after too much change in y, I'm going from here to here. But if I want to make the same change in z, okay, just a one change in contour, then I just need to do little bit effort here from here to here. So basically it is too much change in y, then I'm changing 1 in z. Okay, 1 in z after changing too much in y. But by changing little bit in y only, I'm getting the same change which is 1 in z. Are you getting my point? So this is very very important. Okay, this is very very important. I hope you understood. This is very very important, right? That a small change that I'm making, okay, a small change I'm making here in by, and then I'm getting the change in z is 1 here, and if I'm making the huge change in y, still I'm getting change in z is 1. Okay, so that is why I want to keep these z values equally spaced so that I can compare the steepness. So I will tell you why this convention is important. Why this convention is important? Because I want to check that how fast things are changing. So you will get to understand this. Don't worry. Okay, you will get to understand. So let's just directly discuss this. So what I mean to say, let's suppose this is one, this is one graph. I'm just giving you, the view which you can see by if you are standing horizontally. I mean, if you are standing here and graph is like this. I'm not giving you a top view. Okay, I'm just plotting it in 2D. Although the graph is 3D graph, but I'm just plotting in 2D. Okay, just to make you understand a small thing. So suppose this is the graph. Now, now, suppose I want to draw the contours. So I will be cutting it. Okay, I will be cutting it, isn't it? Now, if I cut it, okay, if I cut this here, and then if I cut this here, and then if I cut this here, then what's going to happen? You are going to get some curves like this, right? So you see here that these two curves, right? These two curves are far. So here I'm having the equally spaced, which is 500. Okay, these two curves are far. I mean, here at this particular point, this is far, right? At this particular point, this is far compared to the same curve here. Okay, this difference is also 500. Here also I have 500 difference. See, at both the places I have 500 difference. Is this understood to everyone or not? At both the places. But if you have to change x or y, okay, whatever you want to change, let's suppose you're changing in x direction, then just a small change in x direction here at this particular point, just a small change in x direction, giving you 500. But here, okay, larger change in x direction giving you 500, right? I mean, change of 500 in z. So which means what? Which means that at this particular point in time, it is lazy, or you can say it is very, very much horizontal type. It is not steep. It is not very much inclined, right? But here the slope is steep. If the slope is steep, then the curves will be these contours will be closer to each other. So basically by seeing that, okay, if it is close to each other, then you can say that, okay, at that particular, originally the slope, you can tell whether the slope has been steep or the slope is not steep. Okay, so here it is not steep as much as compared to here. Okay, so just by looking at contour, you can say that, okay, at this particular point the slope has been steep. Compared to steep means that much inclined. So basically here it is very inclined, right? I mean, or you can say that it is very much steep. Okay, I don't have any other word for steep, but I think you understood, right? The slope is more here, right? Slope is more here. Okay, this is the highest slope you can get, and this is the lowest slope you can get, which is horizontal. So here that slope is definitely more. So have you understood what I'm trying to say? Okay, I hope you understood, right? So basically, what I'm trying to say here is that if the contours, let me just tell you some other example. Yeah, probably this example only. If the contours are closer to each other, it means what? It means here the slope is higher. Originally, the slope is very higher compared to this. Okay, compared to this point. So this is what I want to convey. Now probably we can see some question, and then you can directly solve those questions, and then you can understand this particular topic more. So suppose this is the question that I have. I will also solve the question which I have given the AIMT. Okay, I've given one question in the AIMT related to contour. I think, yeah, this is one question that I've given in AIMT related to contour. We will also solve this question that I've given in AIMT. Okay, suppose that you have this contours. Okay, these contours. So maybe I can. Okay, let me just delete it. Let me just zoom in contours only. These are the contours of some function. Okay, cool. I hope you are able to see this. Let's just answer each question one by one. The first question is that if a person were walking straight from point A to point B, would he or she will be walking uphill or downhill? So they are asking if you are going. This is 0.25 by the way, and this is 1. These are the Z values. Okay. So if you are going from A to B, are you going downhill or uphill? Can you tell me? If you are going from A to B, are you going downhill? Are you going down in the real function, or you are going up? See, these are the values of Z, right? If the original value of Z is 0.25, so it means that you're going from Z equal to 0.25 to 1, right? To Z equal to 1. It means in original you are going uphill, right? Although it seems like you're going downhill, but it's not like that. So basically, inner circles are having a higher values here. Okay, which is okay. Don't worry about it. You just see that okay, you are going from 0.25 to 1. It means you are going uphill. So you will say that okay, I'm going uphill here. I'm going uphill. The next question is the slope steeper at point B or point C. They want to compare the slope at point B and C. You tell me. Maybe let me just remove this arrow. Yeah. So which is steep at point B? It is steep at this point or at this point. What do you think? What do you think? I think here the contours are closer, right? Here the contours are closer. Visually, you can say that okay, at point C it is steep. Okay, so at C steep. Okay, here uphill was the answer. Now, what is the next question? Starting at C. Okay, the next question is that starting at C and moving so that x remains constant and y decreases. Okay, so you are starting at C, moving so that C is this, right? X remains constant. This is x, which means you want to keep it constant. So which means you will go in this direction, and y is increasing and y is decreasing. Okay, so you will go like this. Okay, you want to go like this. Basically, they are saying if you want to go like this, will the elevation begin to increase or decrease? So they are asking that if you go like this, so you are going uphill or downhill. Okay, this is a simple thing that they are asking. Tell me. So from C, if you are going like this, then the elevation, see later on it might decrease or something, but from C, if you just tell me immediately, okay, immediately it is 1.25, immediately it is 1.25, right? So you will say that elevation is going to increase. Okay, later on it might decrease, that's fine. Okay, I'm not seeing too far. In calculus or in machine learning, I mean, we always have limits, right? It is always limit as tends to 0. In calculus, it starts with this limit, which means we always talk in the neighborhood sense. Okay, we always, the basic definition of calculus is like this. Okay, or you can write x plus h first. X plus h minus fx divided by h, limit h tends to 0. Okay, this is f dash x. You might remember this. Anyway, that's okay. So basically in calculus or in machine learning, we always talk in terms of neighborhood. So basically if you tell me in terms of neighborhood, okay, the immediate what is happening, so you will say it is uphill, or you will say it will increase. Okay, elevation will increase. Let's just solve the last question D. Starting at B, moving uh, and moving so that y remains constant and x increases. Okay, which means you are going like this. Okay, you are going like this. Then will the elevation begin, increase or decrease? So if you are going like this, can you tell me? So from 1, you are going to 0.5. Then what will happen? It will decrease, right? It will decrease. So here it will decrease. So what is the answer? Uphill, steep at C, increase and decrease. Uphill, steep at C, increase and decrease. Okay. So these are the answers here. Great. So most of you have given the correct answer, which means you people are getting it. Okay. You people are getting it. Great. Now let's just solve this question. Let me see if you can answer this question. This question I asked in AIMT 4. Okay. This was question number 20. Okay. So what they are saying, a contour line joins location having the same height above the mean sea level. The following is the contour plot of geographical region. So generally we also have the contour plots for the our machine learning functions, or for the hill area. In hill area also people have the contour plots. So basically this is the contour plot for the geographical region. So they are having 25 interval. So these are equally spaced. So they are saying the contours are equally spaced. If this is 575, then this is 550. Okay, 25 is the space. Okay, for which they are making the contours. Now what they are saying, the path from P to Q is best described by. So if you are going from P to Q, then you are going like are you going up first? See, this is 550 and this is 500. So what do you think? You are going to up or down? You are going down, right? From 550 you are going 500, something like this. Okay, this whole is 500. So I think you are going down first, and then so either this is answer, this is answer. Okay, so then I think from here you are going to, from 500 you are going to 500, that's fine. And then I think this is increasing, so you are going up, right? You are going up, and then at Q I think this is up only. So what is the correct answer? So you are first going down, okay, and then this is 500, this is also 500. So what is this? This is I think increasing, right? So this is, since this is 525 basically. Okay, so then you are going 500 to 525. Then you are going up basically. Okay, you are going up. And then are you going down after that? 525. Then you are going up only. And then yeah, so you are going up, and then you are suddenly going down, right? At the last you are going down. So here from 575 you are going down, right? So up down. Okay, at this last you are going down. So down, up, down. So I think C is the correct answer. Understood? Okay, let me know if you have understood. Okay, great. So by the way, result I think has been published for AIMT. It was 6:30 p.m. So how was your result? Can you tell me how much marks you have got? I mean, if you don't want to tell, that is fine. I'm just asking. Okay, if you want to reveal. By the way, I think this is everyone marking is public, so so it is not hidden from anyone. But yeah, still. Okay, great. So yeah, I think you people have got good marks. So Utkarsh is saying he has not attempted. That is fine. Okay. So let's now move to the next question. This is the next question. The similar question, but they are asking a different thing. Okay. The similar question, but this is they are asking something different. So let's just see that what they're asking. Okay, in this question. So they are saying a contour line joins location having the same height above the mean sea level. Like the description is same. Okay. So there's an exact similar contour that we have. So which of the following is the steepest path leaving from P? So if you are at P, then which could be the steepest? Steepest means that is growing, faster or decreasing. I mean, steepest increasing or steepest decreasing doesn't matter, but yeah, it should be steepest. So if you are going in this direction to T, is this steepest or it is very easy question. So basically, I think you are going to R, that is steepest, right? P to R. Why? Because here the contours are very very close. Okay. So here the contours are very very close. Yes. So people have given the correct answer. Okay. People have given the correct answer. Let me know if there is any doubt here. Hope that is fine. So this is this is the topic is completed, by the way, and this is easy topic only. Do you think this topic is tough? This is a very easy topic. Just a small discussion I wanted to have around this topic. Okay. By the way, this question has been asked in gate electronics. Okay, they have asked in gate electronics in 2017. This is a question from gate electronics. Interestingly, they asked this question as a part of aptitude. Okay, interestingly, they asked this question as a part of aptitude. But here in machine learning also contours are very much used. So we need to study here, as as a part of technical subject. But yeah, contours are one of the aptitude thing for few engineers. Like for example, I think engineers who generally deal with the geographical regions, or for these particular people, it might be some aptitude thing. Okay, anyway. So I think in CBSE syllabus also this is there. Okay, in ninth or 10th class. Okay, I don't exactly remember, but I've seen when I was searching for material for the contour, I've seen, I think, some NCRT or CBSE book. Anyway, is this understood to everyone or not? Let me know. Okay, so I think this is fine, right? Now let's just move to the next topic, which is gradient descent. Okay, so contours was easy topic. Now let's just move to the next topic. So here we will actually see some variations of the gradient descent, and also we will solve many questions. Okay, many questions. And this is one very important topic. I can say we will solve many questions, and I can also say this is one important topic. Okay, let's just start with this topic. What is gradient descent? So gradient descent is one method for solving an optimization problem. Okay, what does this mean? I will tell you. See, suppose this particular function is given, and they ask you that what particular value of x it is like what x minimizes this function. Then you will do one thing. You will do f dash x, and then you will put it to be 0. Can you tell me what is the x from here? X equal to what? See, if you try it, then probably you can say this is 2x log x, or 2x ln x, 2x ln x equal to 1 minus x, something like this, right? So if you try your best, maybe you can say plus x equal to 1, and then if you whatever you try, actually, okay, whatever you try, you will not be able to find out the value of x. So basically I want to know that what x is minimizing this function, but unfortunately this f dash x is not solvable. Okay, I mean f dash x equal to 0, you can say, is not easy to solve. This is not easy to solve. Is this so good, everyone? Let me know. So in this case, what to do? If this is not easy to solve, then what to do? Yes. So basically, in this case, we will be applying gradient descent. Okay, gradient descent will help us to solve these kind of problems, and also the problems which are easy to solve. Also, I mean, gradient descent is a general algorithm. It doesn't matter whether f dash x is easy to solve or not. Okay, so it is a general algorithm which is applicable anywhere. So, but we will be applying to most of the places where it is not easy to solve. Okay, and you can also apply to the places where it is easy to solve. I mean, since it is a general algorithm. So basically, this is called closed form solution. So closed form solution are not always available. Okay, so here you cannot directly find what is x. So this is called closed form solution. So closed form solutions are not always available. So that is why we need gradient descent. Gradient descent works in a way that you are, let's suppose, standing here, okay, which means you have some value of x equal to 5, and let's suppose x equal to 100 is minimizing that function, okay, x equal to 100 is minimizing the function. So you will move towards 100, okay, you will move towards valley, which means you just treat this, this hill, you just treat this hill as a function only. So which means you will try to go down, down, and you'll try to go to the value of this hill, okay, by keep on changing the values of x. Okay, so initially x was 5, which means your starting location is this, then maybe this, then you are going here, and ultimately your idea is to reach to the valley, okay, by keep on changing the values of x. So it is iterative algorithm in that sense. Iterative means you will keep on doing it. It's not like one click and then you are getting the answer. No, you have to, just in a loop. It will run in a loop. You will run in a loop. Okay, so let me just explain that what does this algorithm says. Suppose you have let's suppose this function which is fx equal to x square, right? Suppose you have fx equal to x square, and then you want to know at what value of x this function is minimum. Yes, this is easy function, but still let's just understand with this particular example. So we know that x equal to 0, at x equal to 0 it is minimum, right? I mean at this place it is minimum. Still, let's just see if gradient descent can help us to find out this. Okay, so what we will do, it says that let's suppose you are here, okay, you are here, you can be here, I mean at starting location of yours can be anywhere. If you are here, then let me just go to the next page, and then let me explain, otherwise it will be little bit messy here. Okay, so suppose you are here, in this case, if you want to go to the minima, then will you be going to the right or you will be going to the left? Tell me. You will be going to the right? If you want to go to the minima, you are here, so you will be changing the values in such a way that you will be basically increasing the value of x. But if you are here, in that case you will be decreasing the value of x, I mean you will be going to the left. So basically at this particular point, if you are starting at this particular point, then your algorithm should be able to guide you that go to the right. And if you are here, then your algorithm should be able to guide you that go to the left. Is this understood to everyone, that what I'm trying to say? So basically the job of the algorithm is to make sure that you are guided correctly. Okay, so whether to go to the left or whether to go to the right, this is the job of the algorithm, which is given by the gradient descent. So basically gradient descent says that if you want to minimize the function, then there is a property that I'm telling you, that in direction of grad fx, okay, the function always increases. There is one important property, I'm not going to prove it, but yeah, it's easy to prove, but I'm not going to prove it. Always increases. Basically this proof can be given by multiple ideas. One of the ideas is Taylor series. Okay, using Taylor series I have given in the course, but currently it's not needed. Okay, using Taylor series we can prove it. So what I'm saying, that in the direction of grad fx, the function is always increasing. So let me tell you what does this mean. Let me tell you. See, suppose you have this function. Okay, you have this function, and suppose you are at this point or at any point. So at any point there are many directions possible. If this is multivariate function, then at any point there are many directions possible, right? Is this okay to everyone? So at any point there are many directions possible. Now if I just ask you that at this particular point, whether function is increasing or where to go, okay, where to go to increase the function, then you will say that at this particular point probably you will go here, right? So there are many directions, and probably this direction is basically the direction where the function is increasing, right? Now this direction is given by grad fx. Okay, so whatever is the grad fx, it will give you the direction where the function increases the most in the sense that there could be the direction like this where the function is still increasing, but in this direction it will increase the most. So basically grad fx is the direction the function always increases and increases the most. Or in just one line, if I need to write, then you can say the function increases the most. This is very important property. How many of you know about this property already? How many of you know about this property already? Let me know. So this is very, very important property. So basically there are many, many directions possible, and if I want to know in which direction it is increasing the most, then you will say grad fx. Similarly, if I need to ask that in which direction it will be decreasing the most, then you will say minus grad fx. So in minus grad fx direction, okay, in this direction, so grad, okay, this gradient might not be familiar to you guys, right? Okay, let me first tell this. If there is any issue, you can just let me know. Okay, let me first tell this what is the gradient. But let me write this sentence. In minus grad of x direction, function always decreases. And I can say function decreases the most. So basically grad is nothing but differentiation. Okay, maybe I can just give you the example. Let's suppose this is a function. This is, let's suppose, x square plus y square. Suppose I need to find out grad of fx, grad of this fxy at some point where x is 1, y is 1, right? Suppose at this point I need to find out the grad. So grad is nothing but differentiating with respect to x, partial differentiation with respect to x, and partial differentiation with respect to y. So what is the partial differentiation with respect to x? 2x, and this is 2y. And a point 1 1, it will be 2 2. Okay, if the point is 1 1, then it is 2 2. Is this understood? Let me know. So basically grad is easy to compute, very easy quantity. Okay, very easy quantity. So this grad is actually a vector. This is always a vector that has the direction, right? That has the direction. So basically this direction will tell you in which direction the function is increasing the most, and minus grad of x is the direction where it will tell that the function in this direction function will be decreasing the most. Okay, so basically as I told you that at any given point there are multiple possible directions. Suppose this is grad fx, then here the function is increasing the most. Suppose this is minus grad fx. In this direction, if you go in this direction, function is decreasing but decreasing the most. Now suppose you make a little bit angle with the grad fx. Suppose this particular direction, in this direction increasing or decreasing, in this direction also increasing, because it is very near or very within the 90 degree of grad fx basically. Okay, in technical terms, or in other words you can say it is making the acute angle with the grad fx. So basically in this direction also increases, but not the most. Okay, but not the most. In this direction also increases, in this direction also decreases. Okay, in this direction also decreases, but not the most. Are you getting my point? Okay, so basically what I'm trying to say, that you can tell that in which direction function is increasing or decreasing by using the grad direction. Okay, so now you tell me, if this is in xy, then this grad is basically 2D or 3D or 1D. It will be 2D, right? I mean, the grad space is basically the original xy space. I mean, if this is the input space xy, then grad will be also 2D in the same space. Okay, similarly if I have f x y z, let's suppose as x square plus y square plus 3z, something like this, right? Similarly, if I have a function of 3 variables, then grad will be of how many dimension? It will be 3 into 1, right? It will be del x, del y, and del z. So basically if your input are 3, then grad is 3. If your input is 2, grad is 2, like this, right? Now if the input is just 1, then in this case fx equal to just x square, then grad is just a scalar number, which is just f dash x. Okay, just a scalar. Okay, so this direction or the space in which this f dash x lies is in the x space. Okay, just in the same space. Okay, here xyz space, right? Earlier xy space, in this xy space. Understood? So basically what I'm trying to say here is that suppose you are here, and if you want to know that in which direction to go, okay, see, at this particular point I just have two choices, okay, and since this is only 1D, either go left or right. In this particular graph I have two choices only, but in these kind of cases I have infinitely many possible choices, okay, infinitely many possible choices, right? Currently here I just have two choices, that is fine, okay, I just have two choices, either go left or go right. But you tell me, should I go left or right? Then you will say go to the right if you want to decrease. I want to decrease, right? Now let's just sum up the things that what I'm trying to say, okay. Let me just give you the complete picture so that you can connect all the dots which I have been speaking. See, let's not worry about this, I will write it in a while. Suppose this is the graph that we have, okay. Now let's just consider a case. You are starting, okay, you are starting at some particular point. Let's suppose you are starting at here, okay. Let's just consider a point where you are starting at here. Now you tell me you need to go left or right, then you will say go to the right, right? But how does the algorithm tell? Let me just tell you. You will find out f dash x. What is the f dash x? It is 2x, right? Now at this particular point, since x is negative, at this particular point it is negative, or you can say it is minus 15 or something, right? If this is 7.5 minus 7.5, since it is negative, you will say I need to go, if I want to increase, I will go in the direction of f dash x, which means negative direction, which means this. If I want to decrease, then I will go in the opposite of direction of f dash x, which means minus in this direction, which means it is positive, this quantity is positive, so I will go to the right, okay. So basically this is how my algorithm tell me. It will just check the sign. The algorithm is very simple. This is extremely simple algorithm, but very, very useful. So what is gradient descent algorithm? Okay, gradient descent means we want to minimize the function. The objective is to minimize the function, right? So let's suppose your start point is x1, okay. Let's suppose this is your initial point, start point. You can start from anywhere. Now what is your next point? Or let's just call it x2, okay. X2 might minimize or might not exactly minimize. I mean, it can go in that direction. It means that you can just little bit shift, or you can probably shift too much. So I will just tell about these things. But what is the x2? It will say that you go to, or in other words, to find x2, or let me write in this way, go to the direction of f dash x1. That's all. Sorry, minus f dash x1. So you will be going to this direction. Is this fine to everyone? Let me know. Great. So in this direction you need to go if you want to decrease, because you want to decrease, because in this direction the function will be decreasing, okay. To decrease, we always want to decrease because you want to minimize the function. That's why we always want to decrease. Now you can test it by yourself, okay. So here let's just test it by yourself. Suppose you are here, okay. Suppose you are here. Tell me you need to go left or right. As a human, you tell me. As a human, you know that you need to go left. But let's just see what the algorithm say. So algorithm will say that find out f dash x. F dash x will be actually positive, 2x, since x is positive, so it is greater than 0. But what is minus f dash x? It will be negative, right? It will be negative. So it means you go to the left, negative direction. Negative means you go to the left, okay. And then if you go to the left, it will decrease. Now how much to go? This is the next question. Should you be going just like this, or maybe you need to make a bigger jump? So basically how much to go, which means if this is the x1, right, then you need to go to the direction of f dash x. So basically this is the direction f dash x, minus f dash x. You need to go to this direction. Now how much to go? Basically you will be adding this minus f dash x here, but how much? This is given by alpha, okay. Alpha into this, which means if alpha is high, you will be making a high jump. If alpha is low, you might be making a smaller jumps, okay. Maybe with some example it will be more clear. Let's just do some example, okay. For example, let's suppose you are at here, and then you want to know whether to go to the left or right, then you can take the differentiation, okay, and then take the negative of that differentiation. So let me just tell you some example, and then probably it will be more clear. Suppose you are at initially you are at here, okay, initially you are at here. Suppose you are having the step size as 0.8, okay, which is given by alpha or lambda, whatever. So let's suppose it is alpha. So you are at here. Now, what is the f dash x? F dash x is 2x, which is minus 0.8, right? And what is minus f dash x? It is 0.8, right? Or maybe let me just write f dash x only. Now, what is the x new or the next point, okay, which is x2? It will be x1 plus alpha into minus f dash x. Or in other words, you can say, you can write minus directly, which means this is actually very important formula for the gradient descent. We will be again and again applying this formula. This is called gradient update formula. Okay, so weight update formula, or the update formula, I mean gradient descent update formula. So basically this x2 will be, x1 is minus 4 minus alpha is 0.8, and f dash x at that particular point is also coming out to be, okay, this is not 0.8, this is just 8. F dash x is coming out to be minus 8, right? So into f dash x is minus 8. Okay, so basically minus 4 plus this is 0.64, minus 4.64, which means they are saying that you add something here, which means you go to the right. Okay, it is automatically saying go to the right. Okay, now if the alpha value is more, then you will be adding more. If alpha value is less, then you will be adding less. That's the only difference. Understood? Okay, is this fine to everyone? Now basically, let's just see here that what is happening, that we are basically adding, and then the new value of x1 is coming out to be minus 4. This is 2 into minus 4. Why? What is this 2? We are getting minus 4 into alpha is 0.8 into minus 8. Okay, this is 2. Okay, this is f dash x. Okay, this complete thing is f dash x. This is f. So basically your new point, if you do this, then you will be getting some new point. Okay, you can continue this. You will be getting some new point, which will be minus 4 plus 0.64, which means you are going to the right. Similarly, let's just take another example. Okay, here we will be basically making the complete run of the gradient descent. We will be running the gradient descent completely. Okay, so that you get to understand this completely, that what is happening. Let's suppose this is your fx. Now you do the differentiation, which is 2x. Now let's suppose you're starting at this point, which is 8.7. Okay, suppose this is your starting point and this is your alpha, right? Now let's just see that how you are going to go to the minima. Okay, they have given you a few dots that you might go here like this, but let's just see in reality, is this happening? Okay, so what's going to happen here? What will your x1? It will be x naught minus alpha into f dash x. Alpha is given as 0.2. This is 8.7 minus 0.2 into f dash x is what? It is actually 2x. So 2 into 8.7, right? 2 into 8.7. So basically they are saying that that you go 8.7. It will be 8.7 minus 8. Can you do 8.7 into 0.4? Into 0.4, let me just do it. It will be 3.48. Okay, minus 3.48. So they are saying that now you immediately subtract 3.48 and then you will be here only. Okay, it is a big jump basically. Okay, anyway, just because this f dash x actually was the greater at this particular point, because it is 2x, and if x is greater then f dash x is greater actually, so that is why the jump was big, right? This is a big jump. Now this particular point is how much? If you do 8.7 minus 3.48, then you will be getting 5.22. Okay, so you are at, now the next point is this 5.22. Now how to update to the next point? Let's just see. Okay, How to update to the next point? So you will say your x1 or the new point will be 5.22. Now what is the x2? It will be 5.22 minus alpha into f dash x. Okay, this is a fixed formula. So which means 5.22 minus alpha is given as 0.2 into f dash x is 2x. 2 into x value is 5.22, right? Now can you tell me what is the answer here? So 5.22 into 2 into zero point 0.2, right? So which means 5.22 into zero point 0.4, and then that has to be subtracted from 5.22. So it is going to be 3.132. 3.132. Okay. So which means now the next point is something like this, 3.13. Okay. And then you keep on doing it. Okay. Keep on doing it till you get your 0. Right. Is this okay to everyone, that what we are doing in the gradient descent? Is this a little bit fine? Okay. So I hope this is little bit fine, right? Great. So basically we keep on going closer and closer to 0, right? Now depending on the value of alpha, see, if alpha is 0 0.2, then we are going, depending on the value of alpha, I'm changing our x. Okay, see, the update formula is fixed. X new equal to x old in that iteration, minus alpha into f dash x, right? I mean, it is actually plus into alpha into minus f dash x, but instead of that, I'm writing like this. Okay. So which means for any new iteration which is t plus 1, it is the old iteration t minus alpha f dash x. This is fixed gradient descent update formula. Okay, this is called gradient descent update formula. Okay, this is called gradient descent update formula. Is this fine to everyone? Okay, great. Now basically what I'm saying here is that if the alpha is larger, then your new xt, okay, will be fluctuating. I mean, it will be basically how much to go in that direction. See, this is the direction. You can say this is like this, alpha into minus f dash x, right? Okay, so this is the direction. This is the direction. I mean, I have not taken the unit vector. You can take the unit vector also, doesn't matter. Then alpha will be changing. But yeah, this is basically majorly for the direction only, right? In this direction, I need to go. But how much it is given by alpha? So basically, I first get to know that, okay, where to go, whether to go left or right, and how much to go left or right. It will be given by alpha. Now, if alpha is too much, okay, let's suppose I'm starting from here. Then if you're going to left, then maybe if alpha is too much, then you can even cross your minima, right? You are crossing the minima. If alpha is too much, then you are keep on crossing the minima. Then it may oscillate. Okay. If alpha is too much, let's suppose it is 0.9. 0.9, let's suppose here in this case 0.9 is much. Actually, whether it is low or high, it is a subjective point, right? I mean, it is basically depending on the curve or like this. I mean, it's not like that 0.9 is just a small value and 900 is only the bigger value. No. Okay, it might depend on the curve also. So basically here this alpha is actually seeming to be the larger one. Okay, so basically if alpha is large compared to the previous, see, the previously it was just 0.2. Okay, now if the alpha is large, then it might fluctuate. Okay, it can even cross the minima. You need to go to the left, but how much you are saying, okay, bigger steps if you are making, then you are crossing the minima, then you need to go to the right, but you again cross the minima. Now you need to go to the left, but you again cross the minima. So it might oscillate. Okay, is this fine? Let me know. Okay. Okay, so I hope this is fine. Now now let's just go to the same example, but I'm having a more alpha here. Now it seems that it is even interesting case. Can you see that why it is interesting? Can you see why this is interesting? What is the difference between earlier and this one? Here and here. They see here ultimately I'm going to the minima, right? But here, are you going to the minima? Are you going to the minima? No, right? So basically, if alpha is even larger, you might even oscillate and you might even, never get the minima. It might also happen. Okay. So that's why it's very crucial to choose the value of alpha. It might also happen that you may not ever get the minima. So basically, you may keep on fluctuating. You may not get even the minima. So what they are trying to say that if alpha is less, you may progress very slow. You need to go in that direction, but there is a step size, then it's very slow. Okay, just like an ant, right? Too slow convergence. If alpha is less, if alpha is more, you can even overshoot or even diverge, right? So that is why it should not be even slow, it should not be even that much fast, it should be, you can say, I mean, enough to basically making the steps, but not very slow, not very fast. It should be optimal. Okay, just right, it should be just right. Let me know if that is fine to everyone. I hope you understood this, right? So basically, the value of alpha is actually important. Some people call it alpha, some people call it eta or like that, right? So this is the update formula. So basically, let's suppose you are having, we will be solving the question, but I'm just telling you in advance. Let's suppose you are having a loss function, okay? For let's suppose linear regression, okay? Let's suppose this is a loss function for linear regression, and we have the direct formula in the linear regression case. So suppose the linear regression is like this, right? Xw minus y, xw minus y square. This is the formula for the loss function. Okay, suppose. Now in this case, we know if I minimize this, then it will be same as the solutions of this, right? Okay, which is x transpose y. And if this is invertible, then you can have the direct formula like this. I mean, you do not need to apply the gradient descent here because we have the direct formula. But suppose we apply the gradient descent, then can be, yes, we can definitely apply here. Now how to update these w's? Then the similar way, w equal to w new, sorry, w old plus alpha into minus grad f x. So basically we need to go to the direction of minus grad f x, right? Alpha is always positive. This is a step size, it is always positive. Okay, always greater than 0. Understood? It is always positive. So we will be going in the direction of minus grad f x. So basically, this is the very important formula. Okay. So currently we have seen the gradient descent in just 1D case, but we can just see the same thing in the 2D case also. Okay, the same thing in the 2D case also. So let's just see gradient descent or the same thing in 2D case. So the update formula remains same. Okay, where alpha is called the step size. Update formula will not change. Let's just see with this example. Let's suppose you have f x1 x2. This is a 2D function which is x1 minus 1 square plus x2 minus 2 square. Let's suppose this is a 2D function, and now you want to apply the gradient descent here. Okay, suppose you want to apply the gradient descent here. Then how to do it? Let me just show you. Just a second, let me remove the unnecessary things. Suppose you want to apply the gradient descent. They should be giving you two things. Can you tell me what are the two things? What is the initial, initial values of x1, x2? What is the starting point, and what is your alpha? Okay, they should be giving the 2 points. X1, x2 is what? 0, 0. They have given it. Okay, they have given that. Okay, this is the starting point. And what is alpha? Alpha also they have given, which is 0.1. Okay, now we can solve this question. Now before solving the question, let me write the grad. It is 2 into x1 minus 1. With respect to x1, it will be the case this is constant, and with respect to x2, this is the case, right? Okay, so what is the update formula? So the x2 or the next iteration, the x new, will be x old, which is starting with 0, 0, which means this is 0, 0, minus alpha into f dash x or grad f. Okay, or in other words, it will be 0 0 0 0 minus alpha is 0.1 into, if you put 0 0 here, it will be just 0 0, right? Oh, sorry, it will be not 0 0, grad is not 0, it is minus 2 minus 4. Okay, minus 2 minus 4. Is this fine to everyone? So your new point will be 2.1 and not 2.1. Your new point will be zero point 0.2 and zero point 0.4, right? New point will be this. Is this fine? Let me know. So this is not tough question. This is easy question only. You just have to apply gradient descent in 2D. Okay. So the update formula will remain same. It's not like that update formula will be changing. So 2.2 and 2.4 is your next iteration answer. Right. So let's just check. So 0.2 and 0.4. So 0.2 and 0.4 is the next. So they are just asking the answer for the next iteration. Let's suppose they ask for one more iteration. Then can you solve for one more iteration? Yes. How? 0.2. This is 0.4 minus alpha into f dash, or maybe let me write grad fx, right? Grad fx, which is nothing but 0.2, 0.4. Alpha value is given as 0.1 and grad fx at that particular point, which is 0.2, 0.4. Okay, it will be 2 into 0.8 and 2 into, if this is 0.4, 1.6. Okay, so this will be 1.6 minus 1.6. So it, because it will be minus, and this will be 3.2. So minus 1.6 and minus 3.2, I think, right? So let me write it. So it is minus 1.2 and minus 3. Minus 1.6 and minus 3.2. Actually, you just need to calculate these values, okay, and then you can solve for this. So you can have as many iterations as you want. Is this fine to everyone? Okay. So one of the student is asking, can we use gradient descent for any optimization problem? Yes, we can use gradient descent for any optimization problem. Okay. So basically, his question is this. Yes, it is. It is. I mean, it is a way to solve the optimization problem, which is unconstrained. Okay, so there are constraints. Then you have to basically use KKT and all. But yeah, if there is unconstrained like this, then you can definitely use it. Okay, you can definitely use it because it's very simple. It will just say that x new is nothing but x old minus. Basically, it is plus into like this. Okay, but I'm writing in the minus way. It is actually like this. Okay, this is the direction, this is the step. Okay, or in other words, you can even write like this. Okay, so this is very important formula. So the answer of this question is yes. Now we have already seen contours, right? So this is a contour of some graph. Now let's just see. Now I mean, let's just mix the contour and the gradient descent. Okay, which means, let's suppose if I'm starting from this, and let's suppose this is the minimizer. Okay, which means the values are decreasing if I'm going innerwards. So this inner circle is assuming that inner circle is the lowest. Okay, lowest one. Okay, this inner point is the lowest point, and this is the point I want to achieve. Okay, this is the point I want to achieve. So suppose you're starting from here, then the next update, let's suppose, is taking you here, the next update taking you here like this, right? So it is taking you like this. So this is how it is happening in case of contour. I mean, you can visualize this in case of contour. So you are starting with W0, then W1 is basically giving you some updated W1 is this, which is basically this combination of W1 and W2. This is the next point, and then this is the next point, like this, right? So you will be keep on getting the next points. Okay, now let's just see the same thing. Okay, the same thing with the specific objective function. What is the specific objective function? MSE. Okay, let's just see the same thing with MSE, which means if I have mean square error, or if I use a linear regression, then how does this gradient descent work? Okay, this diagram is just to, just to look the slide good. Otherwise there is no use of this diagram. Okay, so don't think that this is very meaningful diagram. It is just to look the slide good. Okay, So for the linear regression, we already have closed form solution, which means we have the w, which is directly given as x transpose x inverse x transpose y. We directly have this w. Okay, we already have closed form solution. But we can also solve the linear regression objective, which was loss function was xw minus y. Okay, we can also solve this using the gradient descent. Okay, we can also solve this using the gradient descent. If we directly solve, then we will getting these equations, and then we will getting this w. But we can also solve using gradient descent. Let's just see. Okay, so basically we will be updating our w, and since there are many w's, so basically we will be updating our w naught, w1 like this. Okay, let's suppose there are wd, then we will be updating each of this w like this. Okay, or in other words we will be updating the vector. Okay, so which means this is the old vector, sorry, this is the new vector, and this is the old vector. So you can say this is w old, this is w new, will be w old minus alpha into grad fx. Okay, the same thing we will see the example, don't worry, we will see the example, and then you will get to understand this very clearly. Okay, what I'm trying to say. Okay, okay. So Anshul is asking something in comments. He is saying that, sir, I had AMT today and it was very good. So but can you tell me where can I learn this bias? So actually this bias, I told in one of the lecture in machine learning, and the lecture name is bias variance trade-off. Okay, the lecture name is bias variance trade-off. There you can see the mathematical formula of bias. Okay, so bias variance trade-off is a lecture where I've told the mathematical formula of bias. So using that particular formula, you can solve the question that I have given today in AIMT. Okay. So, so basically what I'm saying, that you need to update all of these w's, or in other words, you can update a vector. Okay, directly in the vector format, it will look like this, or you can write like this. Okay, where w's are the vectors. Okay, this is a vector, this is a vector, this is a vector. This only alpha is a scalar, everything else is vector. Okay, everything else is vector. So now let's just solve this question. In this question, they have given the loss function. This loss function is basically for the linear regression. Okay, let me just remind you that what is this loss function. Maybe you will recall from the previous discussions. So basically, this is, let's suppose for m points. If I have m points, then for first point, what is the prediction? This is a dot product between w and x, right? So this is the prediction for the ith point. You can say for the prediction for ith point, and this is a scalar quantity, right? And this is also the scalar quantity, so they have written in this way. If you want, you can write in this way. In the vector format also you can write like this. So these two are actually same, these two are same. Okay, this is a vector, this is a vector, and then this whole thing is a vector, right? If the norm, I mean, if you take the length of this vector and then take the square of that, then you will getting the same thing. I think I told you that if the vector is v1 v2 v3, then, and that is v, then basically norm of b square equal to b1 square plus v2 square plus v3 square. So actually these two are the same notations. Okay, and you should be able to write this in the sense that at least you should be able to convince yourself that if you need to write in the summation format. Okay, what is the prediction, what is the real is y, and what is the prediction for the ith data point? It is basically w and xi dot product, right? W and xi dot product, that's all. And these both are scalars, so this is the whole square, I equal to 1 to capital N, if capital N are the number of points, or small m is the number of points, depending on number of points here are capital small m. Okay, you can write 1 by 2, or these things doesn't matter, this is constant only. Okay, now what they are saying, that what is the correct expression for the partial derivative. So they are just asking for the partial derivative with respect to wj. Okay, so they are just asking the partial derivative of this j with respect to some wj. So that is the question that they are asking, right? Okay, so suppose this is j, that's easy only. Del j upon del wj they are asking. Okay, now see here, here you have, here you have, in this dot product you have w1, or let me start with w0 plus w1 x1, you have w1, you have w2, and you have till, let's suppose these are the d features. Okay, you have wd. Now suppose you want to differentiate with respect to wj or some other w. Okay, doesn't matter. So suppose you are having differentiation with respect to wj, or maybe let's suppose with respect to w1. Then what will you do? You will writing 2 into this same quantity. Okay, so don't worry about this summation. You can just put the summation as it is, right? Don't worry about the summation. Now it will be basically I equal to 1 to m 2 into yi minus, right, the whole quantity w transpose xi into, or if you are a little bit confused, then you can write, okay, you can write like this: 2 into yi minus the whole thing w naught, okay, plus w1 x1, like this, right? So basically the point here is that it will be 2 into yi minus w transpose xi only. Okay, into the differentiation of this, right, differentiation of this with respect to wj, this is 0, and here only one of the term, okay, only one of the term, which is basically let's suppose this is wj xj, only one of the term which is wj xj will be active. Other than that everything is basically 0, right? Everything is 0. Now here into this is, since it will be negative because of this negative signs, so this into minus xj, right? That's all. So what is the correct answer? Sorry, for the ith data point it will be ijxj. For the ith data point it will be ijxj, because I'm talking about the ith data point. Okay, so it is x11 x12, I mean for the ith data point it is xi1, okay, i1 i2, like this. Have you understood? Yes, so b is the correct answer here. It is easy to differentiate, right? So I I'm good to see that many people have given the correct answer. Okay, great. Now let's just move to the next question. Okay, yeah, this is little blur. I'm sorry about it. Next time I will just take care of that. But yeah, this is little bit blur. But you can just check that if you just open this up, and if you just see this, then you will be getting B as the correct answer. Okay. Now actually this gradient descent is slow. It's just like elephant. Why? Why this gradient descent is slow? Let me just tell you. See, the gradient descent update formula is like this. It is little slow. See, let's suppose this is your train loss, right? So your train loss will be always like this summation of all the quantities, summation of all the quantities, in the sense all the uh, samples or all the examples basically. So let me write here. Okay, so this is the loss, this is the loss for your data, right? Or you can say it is a train loss, right? Just for the nomenclature I'm calling this is a loss for an individual point. Okay, this is the loss or the squared error for the individual point. For one point it is that. Okay, for ith point, it is the loss. This is the loss for whole data. Okay, loss for whole data. Is this okay to everyone? Now what is the update formula? Update formula says that wt plus 1 equal to wt minus alpha into grad. Let's suppose this is j or l, let me write it j only. J, okay, jw. Basically I need to differentiate this. Okay, and which means I need to have the summation. In this differentiation also there will be summation and all, right? So basically I need to compute this loss and then differentiate. So actually for every update, okay, this means if I'm using this JW, the train loss for the whole data, then for every update I have to go through. So basically this loss is for the whole data. So every update requires the whole data loss. This is the problem. Okay, so every update requires whole data loss. This is one problem here. Okay, this is one problem here. Okay, someone is asking what about 2? You can write 1 by 2, 1 by 5, 1 by 10, doesn't matter, because in differentiation it is anyway 0, right? I mean, these constants doesn't change. Even you can take log if you want, right? If you want, you can take log. I mean, if you're, as long as if you're increasing the function, uh, I mean, this these at least for now these constants actually doesn't matter. Okay, as long as you are having positive constants. Obviously, if you are changing the sign, it will matter. Okay, then the things will change. But as long as you are having the positive constants, it won't matter. So here, what I'm saying, that every update formula requires that whole training loss. This is a big drawback here. Okay, you need to compute the loss for all the training, and then you need to have the grad for this. This is the bigger issue. So basically it's just like elephant. Okay, if you treat this, if you write this train loss here, then it is a bigger issue. So it is not a good thing. I mean, it is actually a problematic thing. So each iteration requires the going over all the training examples, expensive when the lots of data. It is very expensive. Okay, this algorithm is very expensive. So they have something called as stochastic gradient descent, just like pigeons. Okay, you might have seen pigeons in my flat also. So sometimes, now currently they are not there, but yeah, it's just like a pigeons or birds. So basically it says that instead of writing train loss here, I will be writing this loss for ith data point or some data point. Okay, so basically here I will be choosing one data point and I will be writing loss for that data point. Only loss for only one data point I will be writing. Obviously, it is suboptimal. It is not that good in terms of the optimality. See, it is just a trade-off. Earlier it is a very good. Okay, you are having the train loss, you are seeing the bigger picture, and then you are making the decision. Right now, here just because you are seeing one data point and you are evaluating the loss on one data point, and then you are making a decision whether to go left or right or up or down, it is not a very good idea, but yes, in practice it works. Okay, so it is a trade-off. Are you getting a little bit what I'm trying to say? Let me know. So basically what I'm saying, that if you can write just for one data point. Okay, you can choose this randomly or you can choose it iteratively. Okay, first you are choosing data point number 1, then data point number 2, like this, right? So generally we do like this only: data point number 1, data point number 2, and for next update data point number 3. So you can do it. It is very quick, it is very good, just like a bird. Okay, it can fly, it is really quick. But I will tell you the drawback of this also. But yeah, it is really quick. Okay, so basically stochastic gradient descent is one of the way. The main, or it's called actually batch if you're taking the whole gradient descent, or if you're taking the whole batch, it is called batch gradient descent or just a gradient descent. Okay, generally people call it batch gradient descent. And there's a midway also. You don't take whole data, you don't take just one example, you take couple of examples. There's a midway also, couple of examples to compute your loss. Examples to compute loss for update formula. Okay, so this is basically batch gradient descent. You're taking the whole batch. Mini batches, you just take chunk of it. Or stochastic is just you just take one of the example. Okay, so basically I will tell you the drawbacks of each of this. So let's just see this diagram. This is the batch, which means you're taking the whole. If you're taking the whole, then the decisions in which direction you need to go and all, the decisions are very guided. Okay, I mean they are not fluctuating. This is very guided. But if you're taking stochastic, if you just based on one example, if you're moving taking the decision, then you see the fluctuation. Maybe I can just go to the next page. Yeah. So basically here, uh, this green one in stochastic, you see the fluctuations, right? It is going up down. It can do anything. Okay, it is too much fluctuating, because just based on one example you are taking the decision. Batch is this one. This is batch. This is the whole batch gradient descent. This is the best one in terms of the I mean in terms of the time it is slow, but otherwise it is the best one. Okay, it is very guided. Okay, very much stable. This is very stable updates. I'm assuming that alpha is not too less or too high, which means obviously updates depends on the alpha. If alpha is too high, then this can also fluctuate. Okay, but yeah, generally it is very stable updates. Here very fluctuating updates. Here it is a midway. Here it is a midway. Okay, is this diagram little bit okay to you guys or not? Let me know. Okay, let me know if this diagram is little bit okay. That's what I'm trying to say. So, so, if I just tell you, again, then you can see it is very stable and very nice updates. Here the updates are fluctuating, but not that much. But here it could be too much fluctuation. Okay, this I've taken from MIT. Is this fine? Okay, great. Now, in AIMT also, in AIMT 4, if anyone remember, in AIMT 4 also we have given one question related to this. Anyone has attempted AIMT 4? Let me draw that question. Okay, let me just check that question if I have that question now, because I can solve it right away. It is easy question only. Okay, currently I don't have. Maybe in AMT 4 or 3, or maybe in. Okay, I think in today's AMT only. Sorry, in AMT 5, right? In AMT 5, not 4. In AMT 5, we have given this question. So, yeah, let me just take that question. So that was easy question only. I mean, after this explanation, it should be easy at least. So let me just tell you the question directly. Yes, I got the question. The question was something like this. So I was having, there was some description. I can just copy that description also. So I'm copying from Google Doc. That is fine. So basically, the question was something like this. Okay. So what this question is saying, that there are two figures. Okay, they want to just ask that whether this path is more likely come from the execution of batch gradient descent or stochastic gradient. They are just comparing batch and stochastic. So obviously this is stochastic and this is batch, right? So what is the answer? Can you tell me? Great. So B is correct answer here, right? B is correct answer. Yes. So it was easy question only. It was in today's AMT. Okay, this question we asked in today's AMT, and what easy question after this explanation, right? So in AMT 5 gate DA, okay, we asked this question. Now let's just move to the next slide. So I mean, the same thing I'm again and again repeating. So if this is stochastic, then it is too much fluctuation. If this is just a gradient descent or the batch gradient descent, batch means the whole batch. Or if I'm just adding gradient descent, then generally it is whole batch only. Okay, then this is very stable updates. Okay. Now let's just solve few questions, and then you will probably understand the things more. Okay. Now let's solve many questions, and by the end of these questions, you will be getting to understand things much more in much more clear way. Okay. So let's just see what this question is saying. After a gradient descent update, the objective function value at weight vector is always lower than the update than before. So once you what they are saying, once you update it, okay, let's suppose w2 equal to w1 minus alpha, alpha f dash x or grad fx, whatever. Okay, so they're just asking you that, or maybe let me write in loss function way. They are just asking you that if you're updating, then this is your loss function before, I mean the value of loss before, this is the value of loss after that, or value of the objective function, need not to be loss, any objective function. Then they're asking that, they are saying that this w2, let me write w2 on the left side, this w2 is lesser than w1. It is always true. What do you think? Is this always true? No, this is false, right? We have seen this. If it depends on the alpha, if alpha is too much, okay, let's suppose you are here. If alpha is too much, and then you can go here, and at this particular point, the value of value of objective function is actually at this particular one, it is too much, right? If the value of alpha is much, if the value of alpha is too much, then you can even cross the minima, and then you can go far away. Okay, your w2 is this, and at this w2, the loss or the objective function is even the greater than the started, whatever you started with, right? It is not always necessary. If the alpha is good enough, if the conditions are good enough, then it is necessary, but otherwise it is not. So that is why it is false. If the alpha is too large, then objective function can increase, right? Can increase after the update. Is this question fine to everyone? Yes. So that's really nice, right? People are giving correct answers. Okay, it's really nice to see the people are giving correct answers, which means you're getting to understand machine learning concepts in a nice way. Okay, in a nicer way, you are getting to understand machine learning concepts. So people are saying false, 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 false. Depends on if I can't say. So that's really nice to see. Okay, now let's just solve this question. This question is taken from CMU, and this is MSQ question. So what they're saying, which of the following are correct regarding the gradient descent and stochastic? Stochastic means only taking only one. Okay, taking only one example for your weight update. Okay, each update step in SGD pushes the parameter vector closer to the parameter vector that minimizes the objective function. They are saying it is very stable. You are going to the minima. You are always going to the minima in SGD. What do you think? It is very stable. So obviously this is false, right? Obviously this is false. Let's just see the next thing. The gradient computed in SGD in expectation is equal to the gradient. Okay, okay, it is little little hard to explain also. This is little complicated question. So what they're saying, the gradient computed in SGD in expectation equal to the gradient computed in GD. So basically they are saying that the summation of the gradients, okay, the whatever gradients you are computing here, you're computing individually, right? You're computing, let's suppose, individually for all the points, and then you don't know that how many iterations you will be running, right? Let's suppose for all the points you're doing it, and let's suppose you do it 100 times. 100 times for all the points, it may be possible. Okay, on average in expectation 100 times for all points, and here basically here you are doing 100 times only, but one time itself is all points. So basically what they are saying, on average, whatever you are computing in SGD, and the same thing you will be computing in GD. Actually, this is true. Okay, don't worry if you have not understood this. But what this is trying to say is that if you run SGD many times, then you will be updating many gradients. So the total will same. The total of the gradients will be same in the SGD and in the gradient. Okay, in the normal gradient descent or in the SGD, the total is same. So basically it is true. Don't worry if you have not understood it much. Okay, the gradient computed in GD has a higher variance than the computed in SGD, which is why in practice SGD converges faster than in GD. So they are saying it is also, this option is also a little complicated. They are saying that gradient computed in gradient descent, okay, GD means the batch gradient descent, okay, has a higher variance. Higher variance means it is keep on fluctuating too much. See, this gradient doesn't fluctuate too much, okay? But the SGD gradient, it is actually other way, okay? SGD gradient is having higher variance. Variance means fluctuation. Gradient has higher variance because it is just based on one example, okay? So that is why it is false, and that is why it is false. So actually, B is correct answer. Somehow the second question itself become like little tricky. So don't worry, okay? Don't worry about this question if you have not understood this. Now let's just move to the next question. What they are saying: when n is large, we typically use a small subset of data set to estimate the gradient, stochastic gradient. Then explain why we use stochastic gradient instead of gradient descent. So they are saying that why we are using stochastic. Okay, can you explain when n is large why we are using stochastic? Can you tell me the reason? What was the motivation for the stochastic? Basically, it is faster, right? SGD is faster. Okay, it can even converge fast. Okay, since it is faster, so little bit progress I will be making, and it might be fluctuating. See, it might be fluctuating, but ultimately it can even converge fast. Okay, it might be fluctuating too much, but ultimately, since this each update is very very cheap, okay, each update here is very cheap, here each update is very very costly. Okay, here each update is very very costly, right? But here each update is very very cheap. Each update is very cheap, so it generally converges faster. Although it may go here and there, it may go here and there, but still you are doing, let's suppose 1 2 3 4 5 6 7 8, you are, let's suppose, doing 20 or let's suppose 50 updates. Okay, here you are doing, let's suppose, 50 updates, right? But here each update is, let's suppose, if there are 100 examples, then each update is equal to 100, 100 examples. But here each update is just equal to 1. So actually it generally converges faster. I mean, there is no rule about it. There is no there is no, you know uh, I can say definite thing that it will do. It will definitely converges faster or something like this. But generally, okay, they are asking in general in practice why we are using SGD, because it is fast. It is fast. Okay, SGD is fast. That is the motivation behind the SGD. Okay, that is the reason why we are using the SGD, because it is faster algorithm. So SGD is faster. So if you look at the level, it converges faster than gradient descent. Is this fine to everyone? Yes. Yes. So you people have given the correct answer. It is computationally cheaper, right, compared to GD. Okay. So when the algorithm converges, the SGD always finds the same solution as GD. See, let's suppose there are multiple minimas. Okay. Let's suppose there are multiple minimas. Then SGD may go to this minima, GD may go to this minima, right? If there are multiple minimas, then then both algorithms will go to the same minima. Is this guarantee? No, this is not guarantee, right? I mean, maybe SGD may too much fluctuate and finally go to this minima, or like that. I mean, there is no guarantee, right? There are many minimas. Let's suppose there is no guarantee. So basically, the answer is false. For example, if there are multiple local minimas, then even, okay, yeah, actually I was about to say this, that you forget about two different algorithms, even the same algorithms, even the two times you are running the gradient descent, then also it is not guaranteed that both of the runs will give you the same minima. So which means the multiple minimas. So one time I'm running the gradient descent, let's suppose from here, then it will likely to converge at this particular point, right? Another time I'm running the gradient descent from the same gradient descent from here, if the initial point is different, then maybe it can converge here. Even the two times same algorithm may not converge to the same minima, right? So even two different runs of the gradient descent may converge to the different local minima depending on the random initial conditions. Okay, so this is false. Understood? It is easy question only. Let me know if that is okay to everyone. Okay. Now let's solve this question. What they are saying. Suppose we are performing gradient descent to minimize the empirical risk of the linear regression model. So empirical risk is basically the loss function. Okay, it means the loss function, which is, let's suppose they are giving by as this. Okay, so here they are using the feature x1, and then here they are using x1 dash. You just treat this as another feature. Don't worry about this square. Okay, they are using x1, and let's suppose x2, and then x1 dash, which is nothing but x1 square. I mean, there are three features. You can call it x3. Okay, doesn't matter. So basically there are three features. Okay, so one of the feature is getting squared. It is still a linear regression. It is still a linear regression. Okay, it is, we will talk about it later on in the polynomial regression. It is, but it is not a polynomial I mean, so you can okay, we will talk about it more, but yeah, you can treat it as a linear regression only. This is a new feature. Just treat it as a new feature. Okay, on a data set with 100 observations, let d be the number of components in the gradient and d equal to 2 for equation number of components in the gradient. Okay, so basically they are saying, what they are saying, let me just tell you, that you have two components in the gradient. Okay, what is the d for gradient used to optimize the linear regression? Okay, it is something else. So just d equal to 2 is for the part b actually. So d is number of components. Okay, so how many features you have, by the way? You have three features. So d will be how much? 3. But you will be having one for bias, or in other words, you can say apart from the features also. Okay, don't worry about it. It is for the some next part. You can say how many weights you have. You just tell me the weights. How many weight vectors? It's a very easy question. They are just asking number of components, right? How many weights you have? You will be having beta naught. One of this is this beta 1, beta 2, beta 3, right? 4 weights. So basically you need to optimize all of these 4 weights, right? So gradient will be in this 4 weights. So basically the gradient will be, one of the component will be with respect to beta naught, another with respect to beta 1, like this, right? So there will be 4 components only. There will be 4 components. Okay, great. So people have given the correct answer. Let's see this. Which of the following statement is true about the optimization algorithms? So they are saying Newton's method. Actually, this is not in the syllabus, so we can just remove this. Okay, let's just talk about the stochastic gradient descent and the gradient descent. Stochastic gradient descent always requires fewer iteration than gradient descent. Is this always true that we will require fewer iterations? See, there is no hard and fast. Like I cannot say always, right? Okay, I cannot say always. So no. So they are saying it can, even with the small step, sometimes increases the loss. Okay, can it increase the loss? Yes, it can. Actually, it can overall increase the total loss. See, the idea is to decrease the loss, but if I'm just looking at one example may not be able to guide me properly. Okay, so yes, it can do this. Gradient descent, regardless of the steps, it decreases the loss. No. Okay. Convex problems means convex function are the functions which have only one. I mean, where the local and global minima is same. So convex functions looks like this. So basically, like just like a ball shape. This is called convex function, like x square. Okay, fx equal to x square is a convex function. Okay, but yeah, you don't worry about the convex function here. Okay, it is not needed for this question. But I hope you understood the other options, right? Okay. Now let's just move to the next question. Yeah, B is the correct answer here, right? So I hope you are now understanding stochastic and the normal gradient descent and the batch gradient descent and so on, right? Now let's just solve this question. What they are saying: stochastic gradient descent will always be at least as computationally expensive as gradient descent. What do you think? It will be at least as computationally expensive? No, right? It is cheaper. That is why we are using. It is cheaper. That is why we are using. So basically, it is false. So either C is answer or D is answer, right? It is false. Okay. Now what is the next next question, the number of update steps in HDD is greater than or equal to number of steps in GD. Actually, there is no hard and fast rule. Maybe HDD can converge faster, or maybe GD can converge faster. So maybe it can converge faster, or maybe GD can converge faster. Number of steps may be greater, maybe lesser. It could be true or could be false. Okay. So actually, the question is that which of the following maybe answer. So it could be true. The next statement could be true or could be false. There is no hard and fast rule about the convergence. Okay, could be true or false. I mean, number of steps, but yeah, it is cheaper for sure. It is cheaper for sure. So this is false, but the next statement could be true or false. I mean, it is cheaper. That is for sure. But it will be having the lesser iterations or more iterations. That is not guaranteed. But yeah, it is cheaper for sure. Okay, is this understood? Okay. Let's solve this question. What they are saying? Which of the following is not a true statement about HGD versus about GD versus HGD? So they are asking about the false statement. Both provide unbiased estimate of true gradient at each step. Tell me. So basically, the first one, the second one, stochastic is not the unbiased. It is basically biased. It is just looking at one example, right? So not both. Okay. So that is why it is false. So do both provide? No. So the second one is just looking at one example. It is biased for that example only, right? Okay. Now let's just see the next option. The memory and computational requirements for single update for both methods scales linearly with number of features. So they are saying that the memory, yeah, this is a good option. The memory and computational requirement for single update for both methods scales linearly with number of features. If we are increasing the features, okay, then what will happen if you're increasing the features in the single update? Tell me. This is a good option. Just think about it. So if you're increasing the features, which means you're increasing the dimension of the gradient, right? You're increasing the dimension of the gradient. Now if you're increasing the dimension of the gradient, then how it is going to impact HGD and how it is going to impact the normal gradient descent? Think about it. I mean, you can take 1 or 2 minutes if you want to. So let me just check the comments. Both will increase. Someone is saying both will increase. Okay. Are you sure? So basically, if we are increasing the features, then what will happen? That's what they're asking. Yes. So yes, that is true. So basically, it is easy question, right? Don't get much confused. So what they are saying for this particular option, see, this particular option is true actually, right? So what they are saying, the number of so basically, if you're increasing the number of features, if you're increasing the number of features, your grad will be basically having more components. So you can say number of components in grad will increase. then yes, both will be increasing, right? So memory and computational requirements for both of the algorithms will be increasing because both are using grad. So this is true. Okay, this is true, but they're asking for false. By the way, for this option, actually this option is not that easy. This A option is also true. So but it is about the unbiased estimator. It is not that easy. So I'm not discussing this A option because this A option is very complicated. Okay, so this A option is not that much easy. So I'm just skipping this A option. Now for the B, it is actually true, and they're asking for the false. Okay, for the B, you will say it is true. So it is true. What about C? The memory and computation requirement. Computation for single update for both methods scales linearly with the number of data points. Okay, so they are asking if you are increasing the data points, then how will it impact? For the if you're increasing the data points, then for the single update, SGD will not change, right? I mean, SGD doesn't care. SGD, uh, SGD single updates will not change anything, right? So that is why this is false. Is this understood? Gradient descent is likely to converge in fewer. Okay, again, we don't know, right? We don't know. So this is not. Um, okay, they are saying likely to converge, right? Likely to converge in fewer updates or iterations than HGD with a properly selected learning rate. So what do you think? Yeah. So basically, since they are saying likely, that is why it is true, right? That is why it is true. Gradient descent updates are stable. Okay, that is why it is true. So these two are true. This is true. This is true. C is the only option which is false. Okay. So C will be false here. Okay. Let's not worry about A because A is not that easy to discuss. This is related to unbiased estimator. Okay. I hope you understood. Now let's just move to the next question. So which of the following is true for the gradient descent? When training, we should not update the bias offset. So they're asking, yeah, that's very important. So actually, we always update. See the weight vector, right? Weight vector that we update, right? So the gradient of L or maybe the weight vector. So tell me, we should not update or we should update the weight vector. Should it be having W naught or not? Actually, some of the students get confused that we should not have or something. We will always have all the weight vectors, right? I mean, we should be updating all the weight vectors, whether it is bias or not. So that is why this is true actually. Okay, this is true. Have you understood? So we will be updating all the weight vectors. It is not like that we will be only updating, few of the weight vectors or something like this. So let me know if that is understood to everyone. Okay. Now let's just move to the next point. Decreasing the learning rate, keeping all other hyperparameter fixed, guarantees that error of our estimated parameter will decrease. So basically, if you are having a lesser learning rate, will this guarantee that okay, loss function will decrease or increase, something like this? Will this guarantee something? So they are saying decreasing the learning rate. Okay, keeping all the things as fixed guarantees that error of our estimated parameters. So basically they are saying that what about LW1 and LW2? Okay, so it is guaranteed that this will be LW2 will be lesser, or maybe in other words this is lesser only. No, I mean how much to decrease? So decreasing doesn't, I mean these things doesn't guarantee. There is no guarantee about the things. Okay, so that's why it is false. There is no guarantee how much you are decreasing. Okay, there is no guarantee. And even you are decreasing too much, then also there is no guarantee. Okay, what is the next point? Gradient descent can be expensive to run on the dataset with larger number of samples. Yes, that is true. It is expensive. And advantage of gradient descent over SGD is that gradient descent required only a single update to converge. Obviously this is false. Okay, not the single update. So A and C are true. Hmm, just a second. They are asking a true statement. When training, we should not update the bias. Sorry, this is false. Why I've taken? They are saying should not. Yeah. So this is false. Okay. I thought they are saying should. This is false. So that is why C is the correct answer only. Okay. Okay. You people have already told me in the chat. I have not seen the chat. Okay. Great. So let me know if that is okay to everyone. Right. So we will be updating all the parameters. So that is why this is false. Okay. Great. Now let's just see this. A larger step size in gradient descent can lead to the faster convergence. Obviously, no, right? I mean, there is no guarantee or something. So, okay, they're saying can lead. Okay, sorry. Yeah, this is a little bit not very good question, to be honest. They're saying can lead. Yes, they may lead. If you are saying may lead, yes, to the faster convergence. Yes, that is true. Okay, that is true, because anything can happen. But yeah, that is not very good question, honestly. Let's just see this. Stochastic gradient descent performs less computation per update than batch gradient descent. This is easy. What is the answer of this? Stochastic perform lesser updates, less computation. Yes, that is true, right? It is easy. That is true. Let's just see this. For a model with k parameters, okay, k parameters you have, k weight vectors, k weights you have, and the data set with n data points and d dimensions. How many iterations in the gradient? How many dimensions in the gradient of the loss? That's also easy. Can you tell me? If you are having k parameters, then k, right? Then k. Okay, there is no other confusion. And if k parameters, then the gradient will be having k w1. I mean, including w naught, there are k parameters basically, right? So all the weights will be there. Okay, so k. Gradient descent is used to modeling, minimizing the loss, right? Easy question. Each iteration of stochastic gradient descent may increase or decrease, right? May increase or decrease. Again, easy question. The gradient of the loss in the stochastic gradient descent is always negative, is equal to 0. Gradient of the loss. No, it is not necessary. The gradient is always negative. I mean, direction could be anything. Okay, need not to be always negative. Always 0. No. Computed on a sample or the subset of the data set. Yes. In stochastic, it is computed on the sample, right? Okay. So that is why this is true. Understood? Let me know if all the questions are fine to you guys. Okay. So which of the setting would most justify the use of stochastic gradient descent instead of gradient descent? All entries of the gradient of the loss are negative. No, the latest yeah, the data set is large, right? Then we will go for the gradient descent. The data was constructed from the sample, random sample. No, the loss function. No, no. So basically, if the data set is large, then we will go for this gradient descent, right? Have you understood this? Let me know. Okay, so this particular question we have solved, right? This question we have solved. So which optimization path got closer to the optimal solution? So basically, they are saying, okay, let's suppose this is star is the optimal. Then they are saying that which is going to closer to the optimal. Actually, it is fluctuating too much, right? I mean, the path is fluctuating too much. So I think for the C, which optimal path optimization path got closer to the optimal solution. Okay, I think we need to just zoom in. It is actually getting stopped here. Let me just see the question, what they have said. Path of the parameters running the star corresponding to the final parameter value. Okay, star is the final, not the lowest. Okay, star is the final. So see, the lowest is here, right? I want to reach here. I want to reach here. So it seems that this is closer to the final, right? Path B is closer to the final. Okay, that was the question. Which optimization path likely to have lower learning rate? This is like very very slow. If you see this, this is very slow. So path A. The sequence of parameters in path A is more likely to come from the execution of. In path A, it is stochastic. Okay, stochastic path A, path B. Hmm. At C, they are saying path A. Just a second. Which optimization path got closer to the optimal solution? Actually, this the star corresponding to the final parameter value. Okay. So again, it is maybe they are saying that this might be distance larger and this might be smaller distance. Don't know. Actually, this is not exact. The question, the good question could be that okay, which optimization path is having learning rate? This is a good question. Okay, the closure. This is little bit ambiguous. That okay, how to see the closure, because if this distance is closure, this is closure maybe. Okay, so let's just not worry about it. Yeah, the sequence of path in path A, basically in path A it is stochastic, right? So B is stochastic, and then this should be the path A. Lower training, yeah, lower to path B की है ना? Why I am taking path A? Sorry, actually I thought that we can quickly rush on this question, but yeah, just a silly mistake happened. So basically for path B it is a very lower, right? It is going very slow for path B. Okay. So now now I have couple of more questions, and all of these questions are actually whatever those questions are there, all of these questions are I have already solved in one of the video. So now see, whatever we have did just now, this is more than enough to solve probably any question that they are going to ask related to stochastic gradient descent, mini batch gradient descent, or the gradient descent. Okay, but if you want to solve more questions, let me just tell you that you can, if that's not needed, okay, that's not needed, but if you want, then let me just tell you that you can definitely check this particular video. So let me just give you the video link. Okay, although that's not exactly needed. So that video is already uploaded on the YouTube. If you want, you can check this video. This particular video is there. Okay, there like other questions are also solved, but that's not needed for us. For us, the basic understanding how all of these gradient descent algorithms, all of these variations are working. What are the contours? Okay, we have also looked at the contours. So for us, this is more than enough to answer any question. Okay, I mean most of the questions, if they ask any question related to gradient descent or the contours, mostly you will be able to answer. Okay, so we have seen contours, we have seen variation of gradient descents. Okay, so these two we have covered in this particular session. Now we will be moving to the next topics, which are related to regularization, ridge regression and all. Okay, but for now this is enough. So now the next topic will be regularization, polynomial regression, ridge regression, these things. Okay, thank you everyone. So now just a small request that if you have understood the things, if you have liked this session, just do a small comment. Okay, if you have understood the things, just comment. If you have understood these variations, if you have understood the contour, just do comment and let me know if you have liked this session. Okay, just please do it. Thank you everyone. Thank you so much.